Hello audience and student. Again, I'm glad we move to the new topic 10, color mode control. That is very important topic and very interesting topic and the most hot topic in the past, maybe for 20 years. I spent a lot of time learning this and I'm spending some time in teaching this color mode control. Okay, let's start with that color mode control. Okay, I have two introductory pages again. Okay, this is my book, and all the technical content covered in this lecture are taken from this reference book. Okay, so if you are interested in this topic, you get this book and read it. Okay, that can be very assistive in understanding everything about this lecture video series. Okay. As you know, I divide the content of that book into 20 topical areas. So there are so many topics, and up to this is for standalone PWM converter. One single source and one single converter and one single load. That is the standalone converter. Okay, now people are using several converters connected in strange manner. It's called DC power distribution system, and starting from 12, and this is some advanced topic about the DC power distribution system. Okay, so if you have good understanding this, you can easily understand this part. Okay, otherwise, then everything is opposite to the previous statement. All right. Okay, so I started posting this basic lecture videos maybe 2 days ago. Okay, I'll be posting that from time to time, and I posted this and this. Okay, they are posted in the last semester. I posted there this topic. In current semester, I'm posting this, and later on I'm posting this and this. Okay, maybe there is a week or two. 1 week or 2 weeks delay between I'm teaching here and posting the video in the YouTube channel. Okay. So now we are here, color mode control, which is the big topic, the biggest topic. Color mode control is the biggest topic in modern PWM power conversion technique. Okay. So I think we covered this in the previous lecture. Okay, this is alternative control scheme, alternative to voltage mode control, called color mode control. Okay, this is the color mode control in the final form or in the engineering form. Okay, that means in the past the origin of this color mode control is different from this. This is the modern form. It is the current form. Okay, it's not the final form. Okay. Maybe later on somebody will invent something, then this form of color mode control can be improved, okay, can be evolved further. All right. So this is the characteristic of voltage mode control, single feedback pass from out voltage, and this one is suited for buck converters only, and in DCM operation it is some problem, and not to fix. Okay. Somehow people invented color mode control by employing additional feedback from the inductor current, and this is applicable to all PWM converters using even the simpler voltage feedback compensation, and one design procedure will fit for all PWM converters, and the performance of the converter will remain the same regardless of their operational mode, CSN or DCM. Okay, so we'll discuss this. This is the outline of this topic for the entire topic 10. Okay, first we'll cover the basics of color mode control or evolution of color mode control from voltage mode control. Okay, maybe I spent 2 lectures on this topic, and there are basically 2 different approaches: analyzing and designing the color mode control. Okay. First one is classical analysis and design. Is classical one. This is the earlier version of this, of the color mode control. And two famous names on this topic is this Dr. Middlebrook, the father of power electronics, and this Fred C.D., which is the second father of the power electronics. There are only two fathers. Okay. So they developed this story, and there is one guy called Ray Bradley, is the English guy. Okay, he studied the sampling effect of the color mode control. We'll go through the details about this later. And from his result, he proposed new design procedure, including this. Okay, this is developed by this guy, Bradley. He was my colleague, and he's running a company, getting a lot of money from the innocent peoples. Okay, this is the guy. And somehow I find out the approach here and the approach here, they are the same. They are the same approach. Okay, and with that approach, you can optimize the design of the color mode control. Okay, this one looks different. This one looks different. They look different, but effectively they are the same. Okay, I proved that their design, proposed design approach are the same, exactly the same. Okay, I'll explain the details later. Okay, maybe he will be sad, very sad, knowing this fact. Okay, he will be happy. They will be happy knowing this fact. Okay, all right. That will come later. Okay, so but you should wait. Okay, all right. So lecture 1 is about the evolution to color mode control from voltage mode control. Okay? So we review the voltage mode control, just fundamental mechanism. Okay, not the details about this. Right, and we'll discuss the earlier form of color mode control. This form is not used anymore, but historically this is very important. And you will see the term of sub-harmonic oscillation that is related with sampling effect of the color mode control. So we'll discuss this sub-harmonic oscillation. And the initial purpose of this color mode control was very simple, to eliminate the ramp function in the PWM process. The reason for that is, in the past, the making this ramp function is not easy. For 50 years ago, there is no PWM IC or anything. So using discrete component, this ramp function was not easy at that time. Okay, so somehow they want to use something in the circuit, okay, which can be replaced with the ramp function. The inductor current is the good candidate. Okay, so initial purpose of this earlier form of color mode control is to eliminate the compensation ramp, the ramp function, PWM ramp. But somehow they found some problem, and they realized they need the ramp function. But purpose is different. In the voltage mode control, the sole purpose of the ramp function is for the PWM scheme. Okay, in here, PWM scheme can use the inductor current, but to stabilize this compensation ramp is necessary. Okay, the ramp function is necessary, so that they call it compensation ramp. Previously, in voltage mode control, is PWM ramp. In this case, I call it compensation ramp. Okay, and finally, I present the practical form of modern color mode control. As I said, some smart guy will appear and will propose a new scheme for the color mode control. Okay, so this is just the block diagram representation of voltage mode control. So voltage mode control is this one. So they perform this PWM with this ramp signal and control voltage. This is the beginning of the ramp. At the beginning of the ramp, the switch is turned on, and at this point, where this V ramp and control voltage intersect, they turn off the switch. Okay, So this is the PWM. Okay. Control law is turn on the switch at the beginning of operational period and turn on the switch and turn off the switch when V ramp intersect V cone. Okay. To regulate our voltage, there is only one requirement. So make ratio of this one, G2, evaluate at DC, the magnitude of this one and the magnitude of this one, ratio of them becomes infinity, then our voltage is always regulated at V reference in the steady state. Okay, so that is the basic. But requirement is this shouldn't be a zero. If this is a zero, something strange will happen. Okay, this is infinite, this is finite, then this ratio is finite. Okay. Okay, so this is a voltage mode control, and the generating this was not easy in the past. Maybe 60 years ago, it was not easy. Okay, so they used the PWM can be generated not only by this ramp function and any periodic piecewise linear function can be used to generate the PWM. Okay, for example, this is triangular waveforms. This is a triangular waveforms. Okay, so this is control voltage and the triangular waveform is increasing, and you turn on switch at this point and turn off switch at this point when this VI, this triangular waveform, intersect with this fixed control voltage. They need a triangular waveform. Okay, but triangular waveform is already there. Okay, this inductor current of any converter in CCM is a triangular waveforms. Okay, so why we develop this from the circuit? We just use this triangular waveforms here. That was the basic idea. Okay, there are many versions of this, but idea is the simple to get rid of the ramp signal from this PWM process. Okay, so use this one. Okay, IL is sensed somehow, and this is considered as a free. It comes free. You are not paying anything on this. Free functional substitute of costly. Costly means hard to implement, expensive. Ramp function was the basic idea of the earlier form of current mode control. And this block is called current sensing network. And this has the gain, constant gain. Dimension of the gain is resistive. Should be resistive. Maybe they can use simple resistor or resistor plus something else. Okay, should be resistive. So current is transformed to VI. If the gain is 1, then this current is transformed to the same form, but this is considered as the voltage. Okay, all right. So CSN is here, and control law is written down here. Turn on the switch at this moment. Okay, so you should have some logic to turn on this and turn off this switch at the peak point here. Okay, when turn on the switch, the inductor current will increase and it hits this V cone, then turn off switch and repeat this. Right? Okay, and this requirement for the DC regulation remain the same. As long as you satisfy this condition, output is always regulated at reference voltage. Okay, all right, but there I'll show this problem. Propagation of current feedback disturbance means you are using this current, right? You are in current mode control. You are using this inductor current, okay? But there is some disturbance is coming in, right? So original current waveform or voltage waveform with the current sensing network gain of the 1 is this black one. So this one is the original one, but somehow disturbance is introduced in this voltage VI prime. Okay, so VI prime, we have this del I. This is error. Okay, disturbance. Then this will propagate to this. It will go on, and at this point, switch is turned off. The slope becomes negative, decrease, and here this time again is turned on. Go on, then this error will be vanished. That means this is stable, this is okay. Okay? If something happens, eventually the error will reduce to zero, so it will come back to the original waveform without any error. Okay? But if you take a look at the duty ratio of this, duty ratio is smaller than 0.5. Okay? This is one period, and duty ratio larger than smaller. I'm sorry, this one, right? Duty ratio is smaller than 0.5. Okay? This case okay. But if duty ratio is larger than 0.5, this is Buck converter or any converter, duty ratio can be any number between 0 to 1. So duty ratio is larger than 0.5 because this is TS. Then duty ratio is this one. It's obviously larger than 0.5. Then this disturbance occurred here. It goes here. Then it decreases. This is turned on again by the command, okay, PWM command. Then it go up and go up. Then error is increasing. Okay, this is a problem. That means what? Converter is unstable. Okay, this is unstable. So this is not a converter. Okay, and eventually what will happen is this will go like this. Okay, after some time it will settles to in these waveforms. You don't have here, right, in your lecture slide. Okay, so this lecture slide will be posted in the LMS site or e-classroom today. Okay, so you don't have to copy everything. Okay, just listen to me. Okay, catch the idea. Okay, I told you once. Okay, I'm preparing this before the semester, but I fixed this morning. Okay, I cannot provide this to you. So I'm revising this my lecture slide every day. Okay. So go to e classroom or OCW site, and later on you will see in the YouTube site. Okay. All right. Then eventually what will happen is this is increased. Okay. And sometimes it is decreased. Okay. Let me. This is the V cone. Oh boy. Okay, so initially it is increased and hit the V cone and decreased here, and again this is the start of this PWM operation, increase and hit this right, decrease. Okay, so this will generate some strange waveforms. Okay, eventually, right, this is increasing, and it happens like this. Okay, maybe it's a little bit different, but this type of oscillation will occur. It will repeat. Okay, maybe the shape will be a little bit different, but this kind of operation is going on. All right. Then this is considered as oscillation, some strange oscillation, nonlinear oscillation. Then period of this oscillation is 2 times of TS. This is one TS, another TS, and oscillation period is 2 of them. Okay. So this T oscillation is 2 times of switching period, and switching then. This is this, and this TS is 1 over Fs. D is 2 is here. This one, okay. Then the oscillation frequency is half the switching frequency. It's called sub-harmonic oscillation. Switching frequency is fundamental frequency. Okay. Twice of that is second harmonic, third harmonic, fourth harmonic, so on, and some strange waveforms have to. Frequency is called sub-harmonic. Okay, so this is the sub-harmonic oscillation, right? So sub-harmonic oscillation occurs when duty ratio exceeds 0.5. Okay, that was the problem. Okay, it puzzled a lot of people in the past, right? So remedy for this, to fix this problem, they introduced this band function. Okay. So to fix that, previously they used this and this. Okay. Previously the V cone was somewhere here, but it has the sub-harmonic oscillation problem in inductor current. So they add this band function additionally, and you add this graphically. Okay. So this is increasing. So this much is increasing. So at this time, the length of this and length of this should be the same, and length of this and the length of this should be the same. Okay? Right? So this is the inductor current waveform, and this is the external lamp function. They added together, which is this composite signal, which sum of this and this control voltage. So when this hit this, then switch is turned off. Turned off here, okay? V ramp is still going on, but switch is turned off here and turned on again here, okay? So with this, their initial attempt to remove the lamp signal in the PWM process is failed, okay? So somehow with this, they can stabilize this converter, okay? So this is the case with the external lamp, okay? So with additional external lamp, the composite signal Vi plus V lamp is something like this, okay? So with this, this is the case with D larger than 0.5, okay? Obviously, this is TS, and this is the on-time period. So D is larger than 0.5, okay? Stable, right? Previously, it generated the sub-harmonic oscillation. Then still, this is okay, right? So they realized that they can use the inductor current waveforms as the member of PWM process, but they need lamp function. So their initial attempt is failed, but they found there is an additional benefit using this. With this, they need additional this lamp. It's called the stabilization lamp. But with that, this solved all the problems of the voltage mode control. They found that later. Okay? So that is the history of this evolution of color mode control. Okay? All right. So this is the previous lecture slide we went through. So I think it's better to review this. You are discussing the evolution of color mode control, how the color mode control is evolved from the voltage mode control. Okay, so this is the final form, or engineering form, or practical form, or current form of the color mode control. First, forget about this part. Assume they are not present here. Okay, then this is the voltage feedback circuit, and this is the current sensing network. So this circle means the current sensing device. Okay, somehow you are sensing the current, inductor current, and it fed to the CSN current sensing network. Its dimension is resistive, so that current waveform is changed. This voltage waveform, and this is shown here. Okay, first just take a look at this. This is the current waveform, inductor current waveform. Okay, and this is the control waveform, V-con. Without V lamp. Okay, initially you are assuming there is a V lamp, and this is down here. This is a control voltage. Then when the beginning of this operational period, we turn on the switch, and at the instant, this Vi signal intersect this V-con, then switch is turned off. Okay, so this is the waveform, right? So this is okay if duty ratio is smaller than 0.5, but in the previous lecture, we found out that if duty ratio is smaller than 0.5, the initial disturbance in current signal, okay, this del Vi is the difference between this stable one and this is disturbance, and this disturbance is diminishing and eventually it disappears. That means this converter is stable, current loop is stable, but if duty ratio is larger than 0.5, this is the initial error signal is amplified, and eventually it's amplified further, and eventually it ends up with these strange waveforms. So this is the final waveform, maybe the final waveform will vary from this. Next cycle will be something different but very similar to this. Okay? So this is called oscillation, very strange oscillation, nonlinear oscillation. This is not sinusoidal oscillation, and oscillation period is, this is one operational period, this is the twice of the operational period, and this waveform is something like this. So period of this oscillation is 2 times of switching period. So is the time period of oscillation is this one. Then it is converted like this. Okay. So TS is 1 over Fs, and oscillation frequency is half the switching frequency. Okay. That is called oscillation. Harmonic oscillation means fundamental frequency is the fundamental frequency, and the second harmonic is the twice of the fundamental frequency, but this is the half the switching frequency. So we call it sub-harmonic oscillation, sub-harmonic nonlinear oscillation. Okay, so this scheme is inherently unstable if duty ratio becomes larger than 0.5. Okay, their initial attempt was to eliminate this lamp signal from this PWM process in the voltage mode control. There is no this current sensing network or anything, but we need this V-lamp, okay, to perform the PWM operation, PWM scheme. But any periodic waveforms, piecewise linear periodic waveform, can be used to generate the pulse width modulation scheme. So one natural choice is they want to use this free inductor current waveforms, okay, without this. Okay. That was the initial attempt, their target, but later they found that becomes unstable if duty ratio is larger than 0.5. That is absolutely unacceptable. Okay. So somehow they include this lamp signal. Okay. First attempt was to remove this, and by finding out this instability, they introduced this lamp signal, and with the lamp signal, so lamp signal is added, this current sensing network output is shown here, this is V lamp, okay? This graph may be confusing to some student, so I moved this to here, okay? So lamp start here, okay? So V lamp is this one, blue curve. Okay, so V lamp is added. So this is the lamp is generated, and this much is added at this point, and this much is added at this point. Okay, then automatically this control voltage increase to this point to produce the same duty ratio. That is the result of negative feedback. So this control voltage with lamp signal is here, and they generate the same duty ratio, but this waveform is stable. Okay. So the upper curve is V lamp. Oh no, V con with V lamp. Okay. So in this scheme, there is no intention to control the inductor current. People call it current mode control, but nobody is intended to control the inductor current. Okay, they never ever dreamed of controlling the inductor current. Okay, and the eventual goal of this scheme is to regulate our voltage peacefully. Okay, without any instability, and smoothly and quickly. Then there is peacefully. Okay, and during that process, they found out this compensation lamp is necessary to avoid the sub-harmonic oscillation, which occur without the compensation lamp if duty ratio exceeds to 0.5. That will be the problem. Okay, so this lamp is called compensation lamp. In the voltage mode control, this lamp is called PWM lamp, because the sole purpose of the lamp at that time was to perform the PWM scheme, Okay. Now this is used as to compensate the lamp or stabilizing lamp. Okay. I'm using this and this alternatively. Okay. It has the same meaning, stabilizing lamp. Okay. Let's confirm that this is the case of this current mode control. Okay. And we investigate the propagation of current feedback disturbance with duty ratio larger than 0.5, which is this case. This is the TS, this is the DTS. Obviously, duty ratio D is larger than 0.5. This is obvious from this graphic. Okay, and the initial disturbance is this much, and when this increase, they hit this value, it decrease, and it won't decrease further because at the next switching period, the lamp will be reduced to here, and the inductor current will be increasing again, so on. Okay, so this initial error is vanished. That means converter maintains stability, even though the duty ratio is larger than 0.5. Okay, but somehow we want to evaluate this, why this is happening. Okay, mathematically or analytically, but we are using some graphical method to understand this. Okay, for that purpose, we need modify the control diagram or PWM diagram of this current mode control a little bit. Okay, assume this is a current mode control with unity inductor current feedback, means the current sensing network gain is 1. Then the waveform of inductor current is same as the waveform of voltage derived from the inductor current. Okay, and this is the control waveforms. This is the inductor current waveforms, and this is the V ramp, and they are added together. So this much is added to the IL, this much, and this much. Okay, so IL is increasing, it attains the peak value, and decreasing, and this is minimum value, and repeating these things. Okay, this is the one representation of this control waveforms, PWM waveforms. But somehow I want to modify this. The way doing this is we move this V lamp, okay? Because there is a plus sign here. So this is plus, this is negative. So we desire to move this thing around. So it goes this way. So V lamp goes plus and negative sign and come back here. Then add V lamp here with minus sign. This minus sign is coming from the negative sign here. Okay, so this is the same thing. Okay, same mechanism with different representation. So consider this. So we are comparing this IL and this is V cone. V cone is here, and this we are adding this V lamp inverted. Then means we are subtracting V lamp here. So when they meet here, switch is turned off, and at this point, switch is turned on again. Same thing, right? If you draw the timing diagram, so they are the same. They should be the same. So this is the same representation with different notation. This one is more convenient to analyze the waveforms. Okay. So sometimes we use this, but this is the exactly same as this one. We just modify something to simplify our analysis. Okay. All right. So this is the detailed analysis of this stability. Looks complicated. Okay. Previously, the original plot was even more complicated than this. So I divide this into 2 pages. So this is the first page. All right. So let me explain this. Okay. This is the control waveforms, PWM block waveforms, and we have 3 different waveforms. SN is this one. This SN is, let me use this black color. It's not black, but something similar to black. This SN is slope of on-time inductor current, okay, or slope of sensed inductor voltage waveforms, okay? But because the slope, CSA gain is unity, they are the same, okay? So this is the slope of the SN, is the slope of IL during on time period. During this time period, this is increasing, and this is the uptime slope, okay? This is the slope of this inductor current or current feedback signal during the uptime period. So this is the on-time slope of IL. This is valid for DTS on-time period, and SF, this means on and this F is off, is the slope of IL for off-time period, which is 1 minus DTS, okay? All right. And you have another slope. Their slope is this one. This is the slope of external lamp signal, compensation lamp or stabilized lamp slope is this, okay? Then we magnified this part, okay, to know the details about this. Suppose this is the initial error, which is very large, okay? So initial error is propagated like this. So this is the regular waveforms like this, but this is the disturbed inductor current waveforms, and SL, SE remain the same, okay? So here, it beats here, then it goes down, all right? So this error is propagated to the here, and we have some graphical construction. So this length of this, which is this one, okay? Del ILK, the current disturbance at case period is this one, length of this, okay? Length of this is this one. This is inductor current, and this is the inductor current slope, and this is the difference in duty ratio, okay? So because of this, one is hitting here, another one is in here, so there is a time difference of del DTS, okay? And from this graphical construction, length of this, and the length of this can be identified as this one. This is on-time slope times this time period is this length, and this is this external lamp slope times this period is this length, and this is the sum of this length, two line segment. So one is shown here. So one shown here is this one plus this one. Okay. So this is this length. Okay, and the length. The error in the next switching period is this one, okay? So this is original undisturbed current waveforms, and disturbed current waveforms, we have this one, the length is 2 here. So this is the variation, disturbance in the inductor current at K plus 1 period. The next period is this one. This is the same as this, okay? This one is moved to here for the graphical construction, and this one is difference between this and this, okay? This large line segment is SF times this one, okay? So SF times this one, and this is SE times del DTS, but it's a subtraction, so we have negative sign here, okay? All right? So this is 1, and this is 2. 1 is the initial error, and 2 is the second error. So to be stable, the error should be reduced. Okay. At each operational period, it generates the smaller error. So for the stability of this system, so this ratio of this is the initial error, this is the second error, then that is by this expression, it is expressed as the ratio of the slope of these waveforms, and this should be smaller than unity for the stability. If this is satisfied, then this inductor current error will be diminished and eventually disappear. Okay? So this is the required condition for the stability. So for the stability, this should be smaller than 1. Okay? This should be smaller than 1. And you rearrange this. So this is expressed by the slope of the compensation lamp, stabilizing lamp, should be given by this number. okay, larger than this number, this is the minimum of stabilizing lamp slope, okay. If slope is smaller than this, you will come up with sub-harmonic oscillation. If slope is same as this, you have sustained oscillation, some triangular waveforms. If slope is larger than this, that sub-harmonic oscillation will be disappear. All right. So this is a criterion to determine the slope of this. Okay. So slope of compensation lamp, stabilizing lamp, should be larger than this. This is fixed by your power stage waveforms. So this is the minimum waveforms. How about the maximum? What is the maximum? Okay. The maximum should be considered also. So most textbook, they stop here. Okay. This is another end of story. Okay. How can large it can go? Is another problem. Okay. And this is a notation. SC is slope of compensation lamp, and SC is slope of IL, or slope of sensed VI, because we are using the CSN gain of 1, so they are the same. Okay. And this slope, this is, I'm talking about the magnitude of the slope. This slope is negative, but we are considering only the magnitude of the slope. Okay. So here is a conclusion. Okay. So stability condition, something unnecessary is here, condition. This is should be gone. Okay. Requirement is this is the initial error, and this is the error after one operational period should be smaller than 1. That requirement is the same as this. Okay. So as I said, there are 3 questions. This is only lower limit. This is the lower limit. So lamp, slope of the lamp, compensation lamp must be larger than this. Lower limit is given here. Then what is the maximum limit? What is the upper limit? Okay. So we should determine this. We will determine this later. So what is the maximum limit? And if the slope of this compensation lamp is very large, problem of excessive means very large, then what kind of problem will occur, and what is the upper limit and the lower limit is given by simple graphical analysis here. Okay. Okay. I will answer this question later, soon. Okay. Let me take one example. So we know this. Okay. This is the one example. There is some converter, not necessary for converter. Any PWM converter is okay. This is a switching period, and D is this one, 2/3. Okay. So this is 0, 1, 2, 3. So SN is increasing, slope is increasing, and SF is decreasing, and the minimum value is 1M, and the maximum is 4M. Then slope. Here is there is 2 millisec. So millisec is coming to the upstairs. So it becomes this 10 to 3, and this is the 3. This height is 3. So this is SN, and this is FF. Okay. Then you evaluate this critical value of this is this number, which is this one, 0.75, 10 to 3, which is the fast slope, and this external slope should be larger than this. Slope of external lamp, compensation lamp should be larger than this. Otherwise, your converter becomes unstable when duty ratio exceeds 0.5. Okay, that is extremely important information. Okay, so this simple graphical construction will offer the precise solution, precise answer to that. So compensation lamp with a proper means proper is okay. Okay, simply okay. So this guarantees stability. But proper and optimal. Optimal means good performance. Okay. So to have good performance, the slope of compensation lamp should be proper, larger than this number, and it has some optimal value which is larger than this and smaller than something. Okay, so this is required for good performance, right? Okay. Then what happens if you use very large SE, right? Then if this one is very large, then it becomes very similar to the voltage mode control. Okay, there are three slopes. One is SN and one is SF. Okay, three of the slope and one is SE. Three slopes are all combined to generate some gain, some these waveforms. But if SE is very large compared to other two slopes, then two slopes can be ignored. Then SE alone is what? This is voltage mode control. Okay. In the voltage mode control, if you think about voltage mode control, there is no CSN. Okay, it's open. That means SN and S off becomes 0. Only this SE is existing. That is the voltage mode control. So we are talking about the current mode control to improve, to solve some problems of voltage mode control. Then it comes back to the current mode, voltage mode control. You are not doing the current mode control. Maybe the shape and the circuit and structure looks like the current mode control. But if you use too large compensation, then this will go to old, previous voltage mode control. Understand this? Okay, let me answer to this is, if you use excessive, very large, unnecessarily large slope of compensation lamp becomes voltage mode control. Okay, which is extremely bad. For many cases, the engineers, they are designing column mode control, but they are using too large compensation slope. Then actually the dynamics wise, it is voltage mode control, not column mode control. Okay, that is the common problem of there. Okay, so this is the end of first chapter of this topic. So we discussed the evolution of current mode control. Okay, initial attempt was to remove the costly compensation, PWM lamp function because they are expensive and not easy to implement in the past. So they tried to get rid of that and using this triangular inductor current to generate PWM waveforms. But that was okay. But if duty ratio is larger than 0.5, the converter confronted with the sub-harmonic oscillation, which means the converter becomes unstable. So they reintroduced the compensation lamp or stabilizing lamp. Okay, so their initial attempt was failed, but later on they found there are many advantages of using additional feedback from the inductor current. Okay, during this process there is no intention whatsoever to control the inductor current. Okay, so inductor current waveform is used to assist something, okay, but not the control. The desire is not controlling the inductor current. The only design goal of this converter PWM scheme is to regulate the out voltage at the fixed value. Okay, that is the conclusion of this section.